Good afternoon, everyone. I'm Sushma, and before I start my presentation today, I would like to thank the conference organizers for this wonderful opportunity. It's an honor to be a part of the special session on sustainable materials and its applications, presenting my results about IG-processed YBCO, produced utilizing the mixture of ytterbium-123 and barium copper oxide as a liquid phase. Today, I'll start off my talk with an introduction, and then the development of melt growth processes. Subsequently, I'll present about the infiltration growth process and its advantages. I'll then show you the bulk materials I've created and explain its characterization and performance utilizing the XRD, SQUID, CM, EDS, and trap field results. Firstly, I would like to speak to you all in regards to quasi-permanent magnets of high temperature superconductor. R. Weinstein et al. Showed a very high critical current density in YBCO sample. Irradiation of textured Y123, Y211, platinum, and uranium resulted in a further increase of JC by 2 orders and predicted that the trap field values would be very high at 77 Kelvin. This prediction was true. Next, a team in Japan, Murakami et al., then trapped 17.24 Tesla at 29 Kelvin, which was the world record. In 2014, the team led by Professor Cardwell has broken the 11-year record by trapping a magnetic field of 17.6 Tesla. Now, I will briefly shift my focus to industrial applications. Superconducting supermagnets are very important in many industrial applications, such as healthcare, transportation, drug delivery system, space technology, and energy production. However, for all these applications, one must need a large grain bulk material with a high critical current density. And to improve on the critical current density of YBCO materials, many have developed several techniques over the years. For instance, the MTG process was done by Jin et al., the modified MTG process was done by Graves, and this method had been further developed, and Murakami et al. Published about the QMG process and MPMG process. Following that, was a method named PMP, and this was developed by Lian et al. The recent development known as the oxygen-controlled melt growth process by Yu et al. Provides one a superconductor with a high magnetic field, which would be around 5 Tesla. And although there have been many developments over the past years, there are still several problems with this method, such as shrinkage, uniformity of Y211 particles, and large pores. Recently, another viable alternative to the MG process had been discovered. And in the top-seeded infiltration growth process, also known as the IG process, copper-rich liquid phases are infiltrated into a porous Y211 preform above TP, which below TP reacts subsequently with the Y211 to form Y123, as described in the equation shown below. The IG process offers a mirror-net-shaped processing of both superconductors with significant improvement in reduced Y211 inclusion size, reduced shrinkage, and reduced porosity, as opposed to those fabricated by the top-seeded melt growth process. In my previous work, I've successfully prepared YBCO material, which is of 20 mm in diameter, with a mixture of ytterbium-123 and barium copper oxide in the ratio of 1:1 as a liquid phase source. So in this process, I first created the Y211 and Y123 by measuring each substance according to its ratio. In the case of Y123, I've centered it twice, once at 890 degrees Celsius and 910 degrees Celsius, according to this temperature profile. On the other hand, for Y211, I centered it thrice at 870, 890, and 910 degrees Celsius. To test the purity of this Y211, I analyzed the results shown by the XRD, X-ray diffraction. As you can see, after each sintering process, peaks of impurities have reduced and peaks of Y211 had formed. Now, I'll focus on the performance of the sample produced utilizing the Y211 I made. Magnetization measures indicated that superconducting transition temperature is of 92.1 Kelvin, and JC cell field was 39 kiloampere per square centimeter. Through EDS data, one can clearly indicate that all elements have distributed in a uniform manner. Furthermore, the trapped field result confirmed the single cone nature of my sample with a trapped field result of 0.12 Tesla at 77 Kelvin, noting the high performance of the superconductor. In this presentation, IG process YBCO superconductors with the different liquid phase sources was investigated by means of varying the liquid phase ytterbium-123 plus liquid in the ratios of 1 to 1.2 and 1 to 1.3 as a liquid source. And note that in order to compare its growth rate, all the samples were produced at a similar cooling rate of 50 hours. As you can see, this is the process in which I created my YBCO's material and my sample arrangement for the top-seeded IG process. Here I have 8 grams of the Y211 powder, and I fabricated 2 samples, which both have a mixture of ytterbium-123 and barium copper oxide as a liquid phase source, one with a ratio 1 to 1.2 and the other with 1 to 1.3. Then I placed a neodymium seed on top of my samples and placed it into the furnace according to this temperature profile. These samples were cooled for 0.5 degrees Celsius per hour. Once I took it out of the furnace, these samples go through oxygenation for 250 hours at 450 to 400 degrees Celsius. And now oxygenation is an essential step, as through pumping the right amount of oxygen into the material, one can achieve a superconductor with a high TC, as opposed to one with a low TC or a metallic behavior. After this, small test specimens with a size of 1.5 to 1.5 to 0.5 millimeters cubed were cut from the bulk and precisely 2 mm below the seed and characterized utilizing the SQUID superconducting quantum interference device. This slide presents an example of the temperature dependence on the normalized susceptibility for the YBCO material produced utilizing the mixture of ytterbium-123 plus liquid as a liquid source in the ratio 1 to 1.3. Now, one can observe a sharp transition with an onset around 91.1 Kelvin. TC0 is 90 Kelvin, thus giving us a delta TC of 1.1 Kelvin, and this indicates the good quality of this sample. Here I have also attached the summary of all process samples. As you can note that the TC onset of all samples are around 92 to 91 Kelvin. Next, critical current density was calculated utilizing the MH curves, measured at 77 Kelvin utilizing the extended beams model formula. As I compare the results of the YBCO material produced utilizing the mixture of ytterbium-123 plus liquid as a liquid source in the ratio 1 to 1.2 and 1 to 1.3, the cell field is around the same range. However, one can note an improvement in the high field performance in the case of 1 to 1.3. To further study the microstructure of these samples, I've used the scanning electron microscopy, the SEM. For the YBCO sample with the mixture of ytterbium-123 plus barium copper oxide as a liquid phase source, the ratio of 1 to 1, one can identify that it's a high density material as it does not show any pores or cracks. Next, in the top right image, one can observe the spherical Y211 particles in a small size with the sample with liquid phase in the ratio 1 to 1.2. The SEM image of the sample with the liquid phase in the ratio 1 to 1.3 in the bottom right corner shows the uniformity of even smaller Y211 particles. And this could be one reason why there is an improvement in critical current performance. Due to the improved performance in YBCO material produced utilizing the mixture of ytterbium-123 and barium copper oxide in the ratio 1 to 1.3 as a liquid phase source, I decided to produce another sample in a slower cooling rate of 1005 degrees Celsius to 980 degrees Celsius for 100 hours instead of 50 hours. In addition, this material is of 20 mm in diameter and was produced utilizing the IG process. From the image, it is clear that the growth started from the seed and grew up to the rim of the sample, which shows its single-grain nature. To further confirm the single-grain nature, trapped field measurement equipment was utilized. Before it was utilized, The as-grown sample was oxygenated for 250 hours at 450 to 400 degrees Celsius. The trap field measurement equipment. To investigate its performance, the sample first went through the field cooling process. And in this process, the sample had been placed on top of an FRP and had been tightened utilizing an aluminum plate. Then a permanent magnet with a field of 0.5 Tesla had been placed on top of the aluminum plate, creating a field. Then the sample was cooled using liquid nitrogen until the sample reached 77 Kelvin, hence the name field cooling process. After 10 minutes, the sample was removed and placed under the probe of the trap field measurement device. The figure clearly indicates the typical single cone nature, which shows that the sample is indeed single-grained. When the Hall probe scanned the sample above 1 mm of the surface, the device showed that the sample was of 2,150 Gauss at 77 Kelvin. On the other hand, when the Hall probe touched the surface of the sample, it was around 3,000 Gauss. In conclusion, the use of the mixture of ytterbium-123 plus liquid as a liquid source in ratios of 1:1, 1:1.2, and 1:1.3 was used to produce the single-grain YBCO material by the IG process within 50 hours. Magnetization results confirmed that all samples were of good quality with superconducting transitions starting at 91.1 to 92.1 Kelvin. The respective JC values at 77 Kelvin were 33,000 amps per square centimeter at cell field and 16,000 amps per square centimeter at 1 Tesla. The YBCO sample is fabricated by utilizing the liquid phase with a mixture of ytterbium-123 plus liquid with the ratio 1:1.3 was able to trap a magnetic field of 3,000 Gauss at surface and around 2,550 Gauss, 1 mm above the surface at 77 Kelvin. The trapped field results confirm the single cone nature of my sample, and the present results indicate that the mixture of ytterbium-123 plus liquid as the liquid source can help to produce the single IG process Y123 superconducting materials and needed further optimization to utilize this material in industrial applications. Before I end my presentation, I'd like to thank the conference organizers once again for this great opportunity. Thank you.
Thank you, Sushma.
Thank you, Sushma.
Any questions? Professor Jack, any questions?
Phone is mute.
Yeah, I was just
Professor Jack, please turn on the sound volume.
Yeah.
Can you hear me?
Yes, we can hear you now.
Yeah, okay, sorry. First, I would like to thank again the Sushma for the presentation. Congratulations.
Thank you.
I just have a short question about the shrinkage. How about the shrinkage of your final samples?
On my final sample, there was no shrinkage as opposed to those that you would find if fabricated with multiple process. So the shrinkage, there is no shrinkage.
Okay, that means you didn't have any pores, it was free of cracks and so on, the microstructure.
Yes. As you can see through
Thank
that. Let me just show you once again. Yes, the scanning electron microscopy. You can see that's very high dense material when fabricated utilizing the IG process. And as you said, there's no cracks or pores when looked into these images.
Okay.
Thank you for
Okay,
listening.
thank you.